All right, can you read out the question? 6. So A yields product, and then they want the order with respect to A.
Concentration of A at 0 minute is 1 mole.
Okay.
And at 1 minute is 0.50. And 3 minute is 0.25.
This one you could just do by sight, actually. Because to go from 1 to 0.5, how much have we lost? Half. How long did it take? 1 minute. That's the half-life. To go from 0.5 to 0.25, how much did it lose? Half. How long did it take? 2 minutes. So the first half-life was 1 minute. The second half-life was 2 minutes, which means what order is it? It's got to be second order. Half-life is increasing. Okay, other questions? 7 was what? Okay. Ammonia decomposes on a hot tungsten wire. The following are the half-lives that were obtained at 1100 degrees C for different initial concentrations. What is the order? So, as the concentration decreases, the half-life gets shorter. So where do we see as the concentration decreases, the half-life gets shorter? What kind of order is that? It's got to be 0 order. As the concentration decreases, the half-life gets shorter. You only have 3 choices. Maybe this is what you're missing for answering 6 and 7. The half-life could be constant. If the half-life is constant, we call it first. The half-life increases as the reaction progresses. We call that second, and the half-life decreases. We call it 0 order. So here, the half-life is decreasing. It's got to be 0 order. That's a half-life. Is there anybody over there at the computer? Were you guys at the computer lab? No? Okay. All right. Does that answer the question? Okay. So that's what you need for those. So you got to this is just looking at the half-life and then determining. Increasing, decreasing, or stays the same. Okay, any other questions? Number what? 17 on the practice test or on the homework? Can you read out the question and we can cover it?
Alright, the first order reaction A in products has a half-life of 180 seconds.
Okay. So it's first order, and then T1 half is 180 seconds?
So, what is the percent of the sample of A? What percent of the sample of A remains unreacted 900 seconds after your reaction is started?
$900 seconds? Is this multiple choice? If this were multiple choice, then I would just guesstimate it. 180, how many half-lives is that? That's about 6 half-lives, 5 to 6 half-lives, right? And so I would just guesstimate it. But this is not a multiple choice, and so I need to calculate it more accurately. And so to calculate this, we need the integrated rate law, which is ln of A at time t over A initial is equal to minus KT. So I could either solve this equation for t, knowing that A at time t is half of A at time initial, or I could just use the half-life equation. The half-life equation is K is equal to 0.693 divided by T 1/2. And so I need to first figure out what my K value is. And so what does it come out to, the K value? All right, so I can just plug it in here. ln of this is equal to minus k, which is 0.00385 seconds to the minus 1, times t, which is 900 seconds. And then I'll raise both sides of the e, so I'll get which is equal to what? Three point four six. 0.0312. Okay. So that's the amount time t over the amount initial. So it's 0.0312 out of 1 initial. And so we can convert that into a percent. This is 312 out of 1 times 100%, which gives us 3.12%. 3.12% what? Well, that's the concentration remaining, and so this is the percent remaining. 3.12% remaining. In other words, it's the concentration left at time t, left over, unreacted at time t. Okay. Was that that was asking for percent remaining? Yeah. Uh-huh.
For 0.693 over half-life of time for t, what did you use? Did you use 30 or
No, 180.
187?
All right, other questions? From the homework or the practice? No? How many points will the test be out of? What was the practice test or the last year's test for? 40? It'll be 50. At least 50.
Plus extra.
Yeah, 40 must, yeah, it's wrong. I'll look at it again, but it's going to be 50 at least. Okay. All right, any other questions? Yeah? Can you read out the problem?
Sure. Use data from the above figure. Also, it uses a graph.
A graph?
Do you want to see it?
Oh, this is from Raheem's worksheet?
Well, he basically does it.
All right, you know what the Arrhenius equation is? Arrhenius equation. So what do we want to know? We want to know A, and we want to know E sub A, right? But we want to figure out what is the activation energy for this process and what is the frequency factor. And so that's two unknowns. And so we might think, okay, we can come up with other equations, but there's another way to figure that out. And that is, if we take the natural log of both sides, so we take the ln of k, this is going to equal the ln of AE, the minus EA over RT, and then simplify this, you know, so we'll get ln of k is equal to, well, ln of E is going to just be E, so it's going to be equal to minus EA over R, 1 over T, plus the ln of A. Okay, this equation is y equals mx plus b, a linear equation, and this is called an Arrhenius plot. An Arrhenius plot is if we plot, you know, y and x. That is, if we plot the ln of k here and 1 over t here, then we see that the intercept here is going to be ln of A. And so from the intercept, we can calculate what A is by taking the inverse natural log. And then the slope of this equals minus EA over R, where R is just the gas constant. And so from the slope, we can get the activation energy. From the intercept, we can get the frequency factor. All right, so what is this? Number 8 says use data from the above figure to determine the temperature at which T1/2 for the first order decomposition of N2O5 in CCl4 is 2.00 hours. All right, one thing is going to change K. What changes K? What changes K is temperature. The frequency factor should be the same for a given reaction, and the activation energy should be the same for a given reaction. And so if I said, I want the K value of blah, 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 at what temperature would that be? So I just solved this equation for T. But in order to solve this equation for T, I would need to know the A value and the EA value. Right? So I could generate a plot like this. To get it. But there's a way of getting rid of the A value. This is a common trick that's done. Do you guys remember the Clausius-Clapeyron equation? Sounds familiar? The Clausius-Clapeyron equation? Not at all. Clausius-Clapeyron equation has to do with vapor pressure. Vapor pressure. Vapor pressure is like this. Do you remember the vapor pressure curves? They're like that, curved up like that. Well, we can fit this. This equation can be fitted to a mathematical function. But there's another way we could deal with this. And the Clausius-Clapeyron equation was Ln of the vapor pressure, temperature 2 over temperature 1. This is equal to minus delta H of vaporization over R, 1 over T2 minus 1 over T1. Does that look kind of familiar? Yeah. Well, that's vapor pressure. We can do the same thing, except in this case we'll call this one K1, and we'll call this one T1. And so K1, T1. And so I see they don't give us the intercept, but it wouldn't be difficult to find out. I mean, we could figure out what the frequency factor is for the given data, but I'm looking at the solution that you have here, and you're doing this to it. If we take ln of K at temperature 2 minus ln of K at temperature 1, then, well, ln of K at temperature 2 is just equal to minus EA over R, 1 over T2. Okay, minus ln of K at temperature 1. ln of K at temperature 1 is equal to minus EA over R, 1 over T1, like that. And then we factor out a minus EA over R on both sides. We get minus EA over R, and then we'll get 1 over T2 minus 1 over T1 here. And then we'll use the property of logs. This is just going to equal ln of K2 over K1. And so this gives us another way. If we know the activation energy, then we can see. Did I talk about the doubling of the rate for every 10 degrees C temperature rise? I didn't solve it, but this would be the equation you'd use to solve it. K2 is 2 times K1, right?
Is there a difference between the 1 divided by T2 minus, no, wait, you wrote 1, your head is blocking me. From what I read online, it was 1 divided by T1 minus 1 divided by T2. Does that order matter or no?
I always do a final minus initial. Petrucci, you see this negative sign?
Yeah.
Petrucci hates that.
Okay.
He dislikes a negative sign here. And so he multiplies this whole thing by -1 so he can get positive EA over R. If he does positive EA over R, then it's 1 over T1 minus 1 over T2. And so Petrucci likes this. I personally don't like this because this is, you know, when I see the log like this, then it's 2 minus 1, you know, using the property of logs, not 1 minus 2. And so I leave it like this, 2 minus 1. When I look at this is still ln of K2 over K1. It should, using the property of logs, this should still be 2 minus 1. But it's 1 minus 2. I hate that. So Petrucci loves this, I love that. And so either way, it doesn't matter because you'll get the exact same answer. So I really don't care. You know, I just don't like this at all. Yeah, it's just my preference. And so I leave it in this form here. Well, you know, for the half-lives are just inversely proportional to the K's. In other words, I can do this. I know that K is equal to 0.693 over T1 half. And so if this is K1, then this would be T1 half 1, right? And so what I'm going to do is I'm just going to substitute this in here. So I'm going to get ln K2 would be 0.693 over T1 half for temperature 2, divided by K1, which would be 0.693 over T1 half for 1. The 0.693s cancel each other out, and then when we're dividing by fractions, we invert and multiply. And so this is going to be the ln of T1/2 for temperature 1 over T1/2 for temperature 2. And so they're asking, use the data above to determine the temperature at which T1/2 for the first order decomposition of N2O5. There are multiple ways of solving this particular problem. This is one of them, is 2.00 hours. And so what I do is, okay, I'd say that T1/2 2 is 2.00 hours. I need T1/2 1, so I need to know the half-life at one given temperature. So it looks like I would have to calculate it. Unless, did they give it to it? The half-life at a given temperature. No. They didn't. So we got to use the data from the plot. All right, so we'll use the data from the plot. We want to figure out T2, but we need to know, we need to know what T1 is and K1 is, or T1/2 1. So we could do that. So from the Arrhenius plot, we get ln of k over 1 over t, and the slope. The slope is equal to minus 1.2 times 10 to the 4 Kelvin. Okay. And so what can we get from this slope? Yeah, this is going to equal minus E sub A over R. And then what else do we need? Well, if that's equal to minus E sub A over R, then we have that here, because this is just going to equal to minus E sub A over R, 1 over T, 2 minus 1 over T1. So we have T1/2 at temperature 2. We're trying to solve for temperature 2 here. But in order to do that and use this equation, we need to know what T1/2 is at some other temperature. In order to do that. And so we need some kind of T1/2 data. Did he give you the data table for this? I mean, did you guys use the data table for this? Okay. So we have different choices here in solving this graph. We can just get a point from the graph and solve that. And so these are our choices. Choice number 1 is this is y equals mx plus b. choice number one is we can extrapolate to y-intercept. This one. Uh-huh. The half-life is 2 hours. Oh, they're asking you how at what temperature the half-life is 2 hours. Did they give you another half-life in the book? Okay, did they give you the half-life at 298? All right, what is T1 and K1? Times what? 10 to the negative 5. All right, the reason is because the reason I was asking, did he give another one, is because we have some choices, but the choices are going to involve manipulating the graph if we don't have a data table. Manipulating the graph is figuring out what the y-intercept is, or reading one of these dots off the graph. If we read one of the dots, like for example, if I read this dot, and I know what the L and a K is, and I know what 1 over T is, then I can solve this for K. And then I can figure out, at this temperature, this is the K value. But I was looking at the dots, and none of the dots lined up with a line, and there are no grid lines in between there. And so this is why I was asking if there's another piece of data. And so what we need is this. Either I'm going to estimate one of these points off this and figure out at this temperature, this is my K value, or I'm going to draw a line like this so that I can figure out the y-intercept, and when I figure out the y-intercept, then I know I can calculate ln of K, I can calculate the K value for any temperature because I know what the slope is. I just plug in a temperature I want, and I know what the intercept is. If I know the intercept, I know the temperature, I know EA, then I solve for K. And so I was asking you if there's a data table or if they gave you additional data, because I don't want to do that. I don't want to figure out what the intercept is because they don't go to 0. I was looking at the plot doesn't go to 0, so I'd have to extrapolate this out and then extend the x-axis, which is a pain. And none of the dots line up with a grid line, and then that would be a pain because I'm just guesstimating between the lines. And so in this problem, you really need one piece of data. And the one piece of data is this, because if we know what K1 is, then we know what T1 half at that temperature is. T1 half at this temperature is just 0.693 divided by 3.46 times 10 to the minus 5. And so what does that come out to here? Times 10 to the minus 5. What was the units on it? Second. Okay, yeah, we're going to have to convert one or the other. All right, so it's 0.693 divided by 3.46. So it comes out to what? Well, just go ahead and give me hours or seconds or whatever. Seconds.
2.00
Times 10 to the 4th seconds? Okay. So if we convert this into seconds, then what is it? 3,600 seconds per hour or something like that? 3,600, so 7,200 seconds? 7,200 seconds. All right, then we have the half-life at temperature 1. The half-life at temperature 1 is 2,000 seconds. And so the half-life looks shorter, right? Or longer. The half-life looks longer here at this other temperature. And so we know what T1 is. T1 is 298 Kelvin. We just solved this equation for T2. We know what EA over R is because that's just the slope. Okay. And so the trick to doing this was to figure out if we need the y-intercept, we wouldn't have to do this. We wouldn't have to do this equation here. You know, because if they gave us enough information to figure out the y-intercept, then I would have done this. If the y-intercept was easy to get off the graph, I would have solved this equation. ln of k is equal to minus EA over R 1 over T plus ln of A. See, if I knew the y-intercept and it was easy to read off the graph, I would have plugged that in here. Right? That's ln A is my y-intercept. I know what EA over R is because that's the slope. I know what K is because they want a K value that gives a half-life of 2 hours. So I'd go from T1/2 to K, plug in the K value here, and then solve this for T. I wouldn't have done this here. And the reason I did this ratio is because I saw that's what was being done here, but you would have to be given at least one K or one T1/2 value for one temperature, which wasn't easy to read there. Okay? And so that was 14.9 from the effects. We usually do this when we don't want to figure out the intercept. If you don't want to figure out the intercept, then you use this equation. If you can figure out the intercept easily, you use this equation because it can be quicker. Okay. So that's Arrhenius. The half-life and K values change with temperature, and so we could see how the half-lives and K values change with temperature by using the Arrhenius equation. All right, are there any other questions? Okay, read it out for me. Or. All right, number 17 is number 17, how would you solve this? Anybody? You solve this for the rate law. We want to figure out the K value and the order. We can't do the method of initial rates because we only have one experiment. And we can't even do the initial rate because this is more than 5% reaction. How did you do it in lab? How do you figure out the order in lab? Graph it. Are you going to be able to graph it on the test? No. So what are you going to do? Yeah. Due to the rate laws. Joy, you have something? Compare the K values, right. Compare the K values that you get from the different orders. So I don't know if you. I did a problem just like this in class. Do you have it in your notes? Let's check. A problem just like this, 3 data points. We use the integrated rate laws, right? Second order? Yeah, could be second order. But how would you figure out what order it is? Compare the K's. If it's second order, then all the K's that we generate should be constant or the same. And if it's second order, then if we assume it's first or 0 order, the K's wouldn't be constant. The K's would be quite a bit different. And so we just compare the K's. What K's do we compare? We'll call this K1 and call that K2. Compare those two. We could do K3. But K3 is going to be the average of K1 and K2, so that's fine. So what's the first step in determining the order? Yeah. Yeah, we'll just figure out the slope. We're going to assume what order first? 0 order curve. What does K equal to for 0 order? Well, it's concentration time t is equal to minus kt plus concentration initial. And so solve this for K. We solve that for K, we get minus concentration at time t minus the concentration initial divided by t, time interval. Not the time, but the time interval. So we analyze the K's, and then what do we do next? We'll calculate the individual K's. We'll calculate K1. Do you guys have this in your notes? Yes or no? It's a problem in the homework? I mean, do you have the one we did in class in your notes? Yeah, okay, so what do I do next? Yeah, 0.89 minus 1 divided by Does this look familiar? And then we just continue, and then we calculate K2, and then we calculate what? Not the K average. We don't know if this is 0 order. We calculate the percent difference. Percent difference is equal to the biggest minus the smallest divided by the smallest times 100. Okay, after we do this, we don't know if it's zero order, then we move on to first order. We rearrange the equation for K and then solve it and then calculate K1 and K2 and the percent difference. Then we move on to second order, calculate K1 and K2, calculate the percent difference. And then the one with the smallest percent difference is the one that's most constant, which it's likely it's that order, right? And so we can get the order based on which one has the smallest percent difference. That goes in here. And then the K value, well, if it's second order, if second order is the smallest percent difference, then we just average K1 and K2. We average K1 and K2 for second order, we'll plug it in here. That gives us our K value. Okay, once we know it's second order, then we have the integrated rate law. And the integrated rate law is 1 over 8 at time t, if this is second order, is plus kt plus 1 over 8 time initial. And so we could figure out, you know, at 60 minutes, what is the concentration at time t? You know, at 60 minutes. Because we figured out what K is based on the average. We know what the initial is 1.00. So we can figure it out. Okay, is that enough to?
Yeah, I got second order for that one.
Uh-huh.
Is that the right answer?
I don't remember. I don't remember this particular one. You post it on Piazza and see, you know, if other people got second order on this one. What was the percent difference for second order compared to first order and zero order?
I didn't calculate the percentage, but like the K's were really similar.
You can't base it on really similar K's because somebody already did that in the morning class. Let's say 940 versus 970 versus 102 versus 112. Which one, which pair is closer together? Well, you look at 940 and 970, it's 30. And this is only 10, so is this pair closer together? Is this pair more constant? No. I mean, because this is 10 out of 100, so that's 10% roughly. This is 30 out of 1,000. 30 out of 1,000 is like 0.3%, right? Something like that. Is it 30? Well, 30 times 100 divided by 1,000 is 3%. This is 3% difference. This is a 10% difference. Even though this one looks closer, these two are actually closer. So if you don't calculate the percent difference, it's easy to be fooled, and I see this all the time. Every semester, people don't bother calculating the percent difference and just eyeball it and say these two numbers are closer together because these two numbers are only 10 apart, these two numbers are 30 apart. And so these two are closer together, but that's not how you do it. You know, you got to look at the percent agreement or the percent difference between them to determine. And so if you didn't calculate the percent differences, then you could potentially be tricked. And so you need to do that. And then, you know what? If you do that, then you have so much more confidence in your answer because, you know, that one gives you pretty close. Let's say the percent difference is really small, then I wouldn't even question. Yeah, if the percent difference is really small for second order, it's second order. That. And so do it that way. Utima? You have to go through all of them, because the other thing that happens is somebody will get zero order and they say, oh, this percent difference is kind of small, 4%. And then they don't bother doing the rest because they say, oh, that's already kind of small. But it turns out, that second order was like 0.1% difference, but they didn't bother going there because they thought it was small enough. You have to do all of them. If you don't do all of them, then how do you know? How can you eliminate it? Because you have no idea what the other percentages are, unless you can come up with some kind of argument why you don't need to do it. But, Uttama, that happens all the time. There are two things on this that happen a lot, and they lose a lot of points for. One, they don't calculate the percent difference, just eyeball it. And two, they just stop, or they guess. Some people will start with zero order. Some people guess, oh, that looks second order, and let's do that, and don't even bother calculating zero and first to eliminate those, and they'll lose a lot of points that way. You have to do all three. You can't just guess that, I didn't expect everybody to answer that on this particular test. I only expected, this particular test, I only expected a small percentage of the class to get it. How would you change this experiment to make the calculation more accurate? Maybe I think about 10% of the class got it, 90% didn't, had no idea. And so, How would you change this experiment to make the calculation more accurate? Yeah, how would you change this experiment to make the calculation more accurate? Larger time interval. That was probably the most common. Just, collect the third data point out here, or more data. And so, two answers I was looking for: more data or larger time intervals. Bigger jumps between there. Because if the data points are clustered right at the beginning, it's hard to tell. Is that a linear line or is that a curve? But if you spread out the data, then it's easy to tell. It's non-linear. But if all the data is clustered right at the beginning, forget it. Okay, or if you take lots of data, then no problem. You're going to increase the accuracy by minimizing the random error. And so those are the two things. So again, only about 10%. That was kind of like a little bonus. That wasn't part of it. So did you have to do it? No, you didn't have to do it. 90% of the people didn't do it in the last. But 10% did it, and they got some extra points. So it was good for them. All right, any other questions on the practice test, since I have it here, 14C? No? Or homework or whatever else? No?
For 16, you just want a general graph or diagram?
Yeah, for 16 it's like this. So you draw, this is called Maxwell-Boltzmann distribution. Show how K changes to T. K increases with T because so if we increase T, distribution changes. This is going to be T high T. So something like this. So increasing the temperature is going to increase the population of higher energy molecules. This equation is from this curve. No. This is the same guy, Boltzmann. Yeah, it's the same guy, but this is a different topic. And this is not the Boltzmann constant. But Boltzmann was very interested in energy, distributions, populations, looking at it in terms of entropy. But where does this equation come from? This equation comes from this curve, basically. It's a mathematical formula. Defines this kind of behavior. Probably last semester I talked more about the Maxwell-Boltzmann distribution. This semester, because it depends, semester to semester. It depends on the particular class or whatever else, or how much depth I go into some of this stuff. Okay, other questions? No? Yes?
Would a similar problem be on the test?
Maybe I shouldn't. Maybe every single problem I should make not the same as this at all. I shouldn't make any similar problems. I'll keep, I can make every question different than this. Would that be more helpful? Then I don't know. If you want, if you don't want a similar problem, I can make it that way. If you want similar problems, I can make it that way. But
What do you suggest to study?
okay, you know what? When I first started teaching, this is years ago, one of my students, who happened to be a teacher also, got very upset at me because my tests were nothing like the homework. It was nothing like the lecture. Because, that's the way I was often tested. I was often tested because the instructor would say, he doesn't want to test us on stuff he's talked about or stuff that you've done in the homework. He wants to see if you could, do something different. And so I grew up thinking that mentality. The tests aren't supposed to be like the homework. They aren't supposed to be like lecture, right? They're supposed to be like a challenge or something, different. And so that's how I designed every test. I made sure that they were different. If I gave an example in class, I made sure my test wasn't the same as that example because I thought, oh, that's too easy. That's like teaching to the test, right? Then I thought, after I talked to her for some time, then I thought, you know what? She's right. She's right, because why am I spending all this time talking about this stuff if I'm not, right? And so this is why I changed this. So this is why I say if you want to study for my test, just study your notes. If you look, that's 90% of the test is the stuff from my notes. You guaranteed an A. If you know everything on the board, you're guaranteed an A, 90%, right? And then maybe a question or two outside, And then I thought that's fair. I'll try to keep my tests in line with what I talk about, up to 90% agreement, so plus or minus, right? And so what do I want you to study? I want you to study the stuff I talk about, you know? That's it. So then, yeah, I changed. I thought, yeah, that's totally not fair. You know, even when I was a student, I didn't like it either. You know. But I thought, in order to prepare one well for, you know, transfer, they needed that. But it's not the case because, you know, I thought back to a lot of the classes I had, not the higher level classes, but the lower level classes. It's all from the notes. All. Even some graduate level courses was all from the notes. The professor never opened the book, basically, and you didn't have to open the book either. You just went straight from the notes and did all right. Okay, well today we're going to do a lab. We're going to do a computer lab, acid strength lab. So let me talk about acid strength quickly here. But you know, this Maxwell Boltzmann, you know, I'll tell you that year. And that's the problem with some of these tests. That particular year, I talked a lot more about this distribution than this year, you know. In Chem 1A, I talk about this a lot more, you know. The Boltzmann distribution is very, very famous in chemistry, and it has that form E, you know, E raised to the -1 over T, you know, some kind of energy in there. It's very famous. You see it over and over again, that kind of distribution. This is also Chem 1A, acid strength. But since what I've found is so many well, what I found is some people cover this in Chem 1A, some people cover it in Chem 1B. Officially, it's supposed to be covered in Chem 1B. And so we'll just insert it here. This is actually the end of chapter 16. And so acid strength, what are the factors affecting acid strength? One, the bond energy, the bond strength. I'll just say bond strength. That's more correct. Bond strength. The weaker the bond, the stronger the acid. The weaker the bond, the stronger the acid. This would be the HX bond, of course. The weaker, the stronger. 2, bond polarity. The more polar this bond is, that is, the bigger the delta plus and the delta minus, the bigger, the better. In other words, the bigger, the stronger. It's going to attract bases more. We don't have much time. I'm not going to spend too much time talking about the factors. The last factor is going to be the stability of the conjugate base. The stability of the conjugate base is going to come from different influences. One would be the inductive effect. And so we'll say charge delocalization. You know, we look at localized charge means the charge is stuck on a particular atom. Delocalized charge means the charge can be spread out into the structure. And in other words, distributed over a number of atoms. And so charge delocalization can occur by the inductive effect, or resonance delocalization. Okay, and the other way the conjugate base can be stabilized is by hydration or solvation, getting water molecules around that. / solvation. Hydration and solvation is the same thing if the solvent's water. All right, so let's take a look at some of these factors that influence acid strength quickly here. If I look at this series, HI, BR, HCl, HF. As far as bond strength goes, the strongest bond is going to be HF. The weakest bond is HI. And so in other words, if we go from bottom to top, we get a weaker bond. Therefore, we'll get a stronger acid. And so according to bond strength, HI should be the strongest acid because it has the weakest bond. Iodine is a big atom. This is an S on hydrogen bonded to an sp3, like say on iodine. And we can look at the charge distribution here. When we have overlapping, this would be a valence bond. Picture this. When we have overlapping atomic orbitals, there's a higher probability in the overlap region for electron density. All right, versus something like HF, fluorine has a very small orbital. The small orbital is going to concentrate that electron density in a smaller volume of space. And fluorine is actually quite a bit more electronegative. So not only is it more concentrated, but fluorine distorts the electron cloud and pulls more electron density towards it. And fluorine becomes more negative, whereas hydrogen becomes more positive. Positive I'm going to map out in blue. It's just this lack of electron density here. If the electron density is in red, then there's nothing to neutralize the positive charge on hydrogen. And so what ends up happening is hydrogen gets a delta plus and fluorine gets a delta minus here. The electronegativity difference here is minimal. And so if I look at the delta plus here on hydrogen, it's very small. And the delta minus here on iodine is very small. And so in terms of bond polarity, polarity increases as we go down because it just becomes more electronegative, like fluorine's much more electronegative. And so increasing polarity as we go down means increasing acid strength. And so according to polarity, HF should be the strongest acid because it's going to have the greatest distortion of the charge. But HF also has the strongest bond, so it's conflicting in this way because if you're a base, let's say water, if you're a base like water, are you going to be more attracted to HF or more attracted to HI? You'd be more attracted to HF because of the positive charge on the hydrogen versus HI. But even though you're more attracted to HF, it's much easier to pluck the proton off HI. And so in this case, if this sp3 orbital gets pushed into this s orbital on hydrogen and try to kick out fluorine's electrons, it's going to have a hard time. Whereas if this orbital here gets pushed into this one, it'll have a much easier time kicking out iodine's electrons. Actually, both of these. So there's one problem here, though, and that is this. We have a conflict. And so who wins? It turns out that HI is the strongest acid. And so even though there's not much polarity here to attract it, well, it's just much easier to pluck that proton off. And therefore, the acid strength goes in this order here. And so bond energy is the dominant factor. HF is 1,000,000 times weaker of an acid than HCl. Does it mean that HF has 1,000,000 times stronger bond? No. No. HF doesn't have 1,000,000 times stronger. HF has a little bit stronger bond, but not 1,000,000 times stronger, not even close to 1,000,000 times stronger. And so why is HF 1,000,000 times weaker of an acid? And the reason is because of this. When HF undergoes dissociation, it doesn't completely break apart. That is, we end up with an ion pair formation. So an ion pair forms, and what you have to do is you have to break apart the ion pair to get the free acid, that is hydronium or H+. And so there's an additional collision required for that to happen. Whereas chloride doesn't really have a big ion pairing problem because chloride's not as concentrated as far as negative charge density goes as fluoride is. And so HF is unusually weak. Unusually weak acid because of ion pair formation. Fluoride's very small, chloride's a lot bigger, you know, so chloride, you know, the most closest one is not going to have an ion pair problem. Okay, then we have let's compare acids with similar bond strength. Acids with similar bond strength would be something like the oxyacids, in which we're looking at the HO bond. Where X might be a halogen or R might be the rest of the molecule. If we look at this, we're looking at breaking the HO bond. 300 to 400 kilojoules per mole to break that, I think. Or actually 400 to 500. And so, in this case, we look at things like polarity or stability of the conjugate base. So let's take a look at a couple of structures here. This would be ethanol. Ethanol is not usually considered an acid. It's considered pretty neutral. It doesn't really react with bases. It could, though. And so this is neutral. If you had a very powerful base, like a super base, then it could pluck that proton off to extremely weak acid. And acetic acid is moderate strength acid. But when we look at this, if we look at polarity, you know, polarity is electronegativity difference. So, you know, oxygen is 3.5, hydrogen is a 2.1, oxygen is a 3.5, hydrogen is 2.1. And so they have the same bond strength, and they look like they have the same polarity. And so should they be the same strength acid? No. Because we look at the next atom. The next atom is carbon. Well, carbon is a 2.5. Carbon's a 2.5. Both of these have carbon. So should we look at the next atom? If we look at the next atom, it's a hydrogen here and oxygen here. Now there's a difference. Oxygen is a lot more electronegative. And so this is what we call the inductive effect. You know, this oxygen is going to suck electron density away from this carbon. Okay, this oxygen is going to suck electron density away from this hydrogen. Now there's a carbon versus oxygen tug of war. If there's a carbon versus oxygen tug of war, who's the winner? Carbon or oxygen? Oxygen. Oxygen is more electronegative. But these two carbons don't have the same electronegativity. They don't have the same electronegativity because of their oxidation states. What's the oxidation state of this carbon here? The oxidation state of this carbon is 2, 4, 5, is -1. So this carbon has a charge of -1 according to oxidation state. This carbon has a oxidation state of +3. And so when you look at these, a +3 carbon versus a -1 carbon are going to have a different pull on electrons. A +3 carbon should have a much stronger pull. And so because this carbon is a +3, it's going to, when it gets into a tug of war with oxygen, it's going to pull a lot more electron density than this carbon here. This carbon's -1, it really doesn't want more electron density. And so oxygen's able to suck some of that electron density here and suck some of the electron density here. And so what we're going to see is this. We're going to see the charge buildup on this hydrogen is much smaller than the charge buildup on this hydrogen. Okay. But the difference in acid strength is orders and orders of magnitude. I think over 1,000,000 times. I think acetic acid is over 1,000,000 times stronger acid, maybe. So does that mean that this delta plus is 1,000,000 times bigger than this one? No, there's got to be another factor influencing acid strength. Because, you know, it's not that huge of a difference. And so, yeah, this is a moderate acid. That should be, you know, pretty weak acid, but maybe it should still be acidic rather than neutral. And so let's take a look at the conjugate bases. And here we can see a big difference in the stability of the conjugate bases. So for my past Chem 1A students, you know, this is all repeat, right? We did this lab before in Chem 1A. And so I don't want you to do it again. What I want you to do is, I want you to do Spartan on all the bases, all the conjugate bases, rather than the acids, and look at base strength instead of acid strength. Everybody else will do acid strength. All right, so for the conjugate bases, we're going to have this. This is called ethoxide. Ethoxide's similar in strength to hydroxide. In fact, it should be because, you know, this is oxygen bonded to carbon. Well, oxygen bonded to carbon versus oxygen bonded to hydrogen. Carbon and hydrogen have about the same electronegativity, you know, 2.5, 2.1. So it doesn't make that big of a difference. So this is a strong base. It's not one of the strong bases you memorize, but it's a strong base. Whereas acetate looks the same. So is acetate a strong base? Because this is oxygen bonded to carbon, this thing looks like hydroxide, but is it? No. It's not. Well, one of the things we might say is because of this. It's because of the, you know, inductive effect. But this carbon's -1, and so this is kind of electron rich. It doesn't really In fact, it's pushing the electron density out. It's an electron pusher. Whereas this one is +3. This is withdrawing electron density. And so both of these oxygens are -1, but what's going to happen here is that some of that negative charge density is going to be pulled into carbon because carbon is lacking. This is the inductive effect, right? That's due to this terminal oxygen. But you know what's more significant than the inductive effect is something called resonance delocalization. Resonance delocalization is a much bigger factor in weakening the base strength of this. Because what can happen is we can draw another resonance form for this. It's going to look like this. And so we can delocalize the charge over 2 oxygens. In fact, neither of these structures is correct. You know, both of these structures are based on valence bond theory. And this valence bond theory, where does valence bond theory come from? Is valence bond theory the most up-to-date theory on bonding? No, what is the most up-to-date theory on bonding? Molecular orbital. In fact, valence bond theory had some significant failures, didn't it? And so, why do we still use valence bond theory? Because it's a lot easier. And so rather than, actually neither of these is correct, the hybrid structure is correct. So let's go ahead and get the hybrid structure from this. The hybrid structure is going to look like this. It's going to be we'll have 2 lone pairs and then 1 lone pair that's kind of floating, both of these, and then double bond. Bond order is 1.5. And so when we look at the formal charge on each of these, it's -1/2 on each. And so what we've done is we've cut the charge on the oxygen, you know, by half. It's going to make it a lot less reactive. You know, bases, they want to seek out protons. Protons are positively charged, so this is going to be much weaker. Not only that, but we also do have the inductive effect as well, because this is +3, I guess, so that can suck in electron density towards the carbon, too. And so acetate is a much weaker base than ethoxide. A weaker base means it's more stable. Okay, weaker bases have more charge delocalization. Stronger bases, the charges are more localized. Like here in ethoxide, can that negative charge be spread out into the structure? No, because you got this barrier here, this -1 on that carbon. And so alcohols like this, the conjugate base are the, you know, like ethoxide or whatever else, they're going to have localized negative charge, which means they're going to be highly unstable. Except for this one. This is an alcohol that's unusually strong as far as its acidic properties go. This is about as strong as acetic acid. In fact, I think it's stronger than acetic acid, but I'll have to check. And so what makes this alcohol so strong? And so if I look at this alcohol, the shorthand structure for benzene ring is like that, but let's go ahead and draw it out. All it is a benzene ring like this with an alcohol stuck on one of the carbons. And so this is unusually acidic. And and it's called phenol. Is it unusually acidic because of the polarity? Well, let's take a look at the polarity. What's the oxidation state on this carbon here? The alcohol carbon. It's +1. +1. Let's see. In ethanol, it was -1. In acetic acid, it was +3. So this is somewhere between. And so it doesn't look like there's much of an inductive effect. Maybe a little inductive effect, making it more polar than ethanol, but less polar than acetic acid. There's a little bit of an inductive effect. And so it doesn't look like polarity is the main factor why phenol is so acidic. In fact, what the main factor is this. It's the stability of the conjugate base. This conjugate base is a bit unusual. Although it doesn't really look that way, because it does look like the negative charge is localized on the oxygen here, right? How can I spread that out? Well, the way I'm going to spread that out is by using non-equivalent resonance forms. Non-equivalent means, they don't have exactly the same energy. And resonance forms is just another way of rearranging the electrons. So if I do this, if I take that lone pair and drop it into this bond, that's going to give carbon way too many electrons. So I'll convert this sp2, this sp2 carbon into an sp3 carbon and throw the lone pairs there. And so I'm going to end up with a structure that looks like this. Lone pair here. And that's going to move the negative charge to this carbon here. Well, that's going to be less stable. So this is going to be a higher energy resonance form. But as far as the hybrid goes, the hybrid is going to be biased or weighted towards the more stable resonance forms. And so the hybrid structure will be more biased towards this structure here, with negatives on the oxygen rather than negative on the carbon. But what we can do here is we can move the electrons more. That is, we can take this sp3, drop it in the bond, create an sp2 there, and then pop these out here. And that results in this resonance form here. Negative charge here. And then we could do that again here. We pop these electrons into the bond here, pop these out over here. Yeah, you'll end up where you started if you do this. If you pop these down here and then pop these out, then you'll end up where you started. And so that's a total of 4 resonance forms. 3 of these resonance forms are equal in energy, pretty much, or close, very close. This one is quite a bit different, but all 4 can contribute to the hybrid. The hybrid would be more biased towards this structure because it's more stable. Right? And so phenol is an unusually strong acid for an alcohol, and it's because of the stability of its conjugate base. This is driving force. Driving force for reactions is you want to go from unstable reactants to stable products. Well, stable products would be weaker conjugate base. Weaker conjugate base means, the negative charge isn't concentrated or localized, but delocalized. The more negative charge buildup, the stronger the base. All right, so I'm going to stop here. We're going to go over into the computer lab, Chem 108, and then we'll start Spartan there.
Like the conjugate base.
Stable.
Acidic.
This,
Very, very stable.
yeah, the conjugate base is stable, or I mean, it's more stable, and therefore phenol is the stronger acid.